So, have you questions for static and dynamic behavior and the theoretical definition and the practical definition with the rest of error? No, that's very good. Then we come to measuring errors. We have already used the expression error also in the definition of the dynamic behavior and the end of the dynamic behavior. But errors is a main point in measurement and instrumentation because errors and uncertainties are the enemies number one for quality. When you would like to produce a high quality, you have to reduce errors and uncertainties in your measurement, in your range, what is accepted for the quality of the products. The definition of the error is y minus x. And you remember, x was a true value. That was a true value, what you have in your system, the true value, the input value. And y is a measurement value. The measurement value, what your device is giving out. And important is also that you say y minus x, because the sign is also important for the error. Have you a negative error or have you a positive error? That is also very important, and therefore you have to use this order y minus x, not x minus y. Then get you a wrong sign. In the ideal case, you see also here, the error is 0 when y is x. And y is x will be also for the calibration of the measurement devices our aim function. Y is x is every time the aim function. The systematic of measuring errors shows that we have two big kinds of errors, two big kinds. We have the random errors and we have systematic errors. And we will later see the definition of the random errors and the systematic errors. The random errors comes unexpected. You don't know when, you don't know the amplitude, you don't know the sign. And when one of these parameters is not known, then is it a random error. In opposite to this, the systematic errors are errors where you know all these points. You know how big they are, the amplitude. You know the sign, is it plus or minus? And you know when they occur. And when you know this all, then can you also correct these errors. When you have a balance and nobody is standing on the balance and there is nothing's on, then should be y 0. But when the balance show a value, 1 kilogram, for example, then you know that is a static value, but there is an error in. There is an error of plus 1 kilogram. And then can you correct this? You can adjust the 0 point. You can calibrate the amplification and maybe also correct the nonlinear function between input and output side. Both kinds of errors have an influence of the static errors and the dynamic errors. But for us, important is the static error, the influence on the static error, because normally when we measure, we have to wait until the dynamic behavior is nearly finished. And so we declare it that we are in the static behavior of the device. But when you have then a difference, then you know it comes from random errors. Normally, you see that the error is changing every time. Then you know that are random errors. And it can come from the systematic errors. And here you can calibrate. The static errors, systematic static errors, you can calibrate. And random static errors, you can only describe with statistical methods. That is the only one chance what we have, because we don't know comes the error the next time again or not. Therefore, I cannot correct him. I can only describe yes, I can only describe the error with statistical methods. And that is what we looking for now. How can we describe random errors? We can describe random errors. At first, we can calculate a mean. We can calculate a mean. You know all how to calculate a mean. And then we can calculate the sample variance. That means that we calculate the difference from a single point to the mean. We power by 2 and divide by n-1. I will declare it later why that is so. And we get the sample variance, but that is the standard deviation powered by 2. And that is for the description of the quality of a measurement row. Is it possible? But you have here the powered by 2 unit of your measurement value. And when you measure, let me say, a length measurement with millimeter, you would like not to describe the quality of the measurement row with square millimeter. You would like to describe them with millimeter. And therefore, in measurement and instrumentation, we take every time the root, and what we get is the standard deviation. And the standard deviation is also a measurement value or a value for the quality of the measurement row. How works it? That is important. And I think I change now to my drawing screen. I hope that works. Let me change, and then can I write a little bit down? So I hope it works. Can you see? Yes. You can see it. That I can write it here. So that is good. Why is that so? Let me say we have 2 measurement rows. One is this measurement row, and we have another one where we have these measurement values. And I think it's clear which one is better. Better is this one. But what have we done? We have looked what is the mean. That is this one. This is the mean. And then have we compared the mean minus the single value. Let me say that is y. That means the mean minus the single value. The single value. Now we are looking for a parameter for the quality. We can calculate the mean over these differences. These differences here are very small and here are bigger. But we have plus differences and we have minus differences. And when we calculate only the mean, then have we the problem that we can come on the same value. But that makes no sense. We can take the absolute value. That would be possible. That we take only the absolute value, and the mean over these absolute values must be bigger than here. But the absolute value is a difficult mathematical operation, and therefore we say we power by 2 these values. We power by 2 these values, and we must only remember later that we take the root of them. But when we power by 2, all the values have a plus sign. Also, these values have a plus sign in the end. And now we calculate the mean over this. The mean from the first until the end. From the first value until the end. We add all these single values, and now we have to divide. But we have not to divide by n, we have to divide by n minus 1. Why have we to divide by n minus 1? Let me make an example. We have 3 following numbers. You can take every number. 3 following numbers. You can also take 14, 15, 16, or what else. The middle is the mean. We have a difference to this one is 1. We have a difference to this one is 1. The mean over the differences is 1. When you power by 2, by the way, it's also 1. The mean is 1. When you take the root from everything, it's also 1. That means the standard deviation from 3 following numbers is 1.0, 1.0. That's the standard deviation. That means you have not to divide by n, you have not to divide by the number, you have to divide by the comparisons to the first value. And the comparisons to the first value is every time n minus 1. And what you see here, that's already the standard deviation. That is a standard deviation. You powered by 2 the differences. You divide by the comparisons to the first measurement value? Of course, it's the difference when you divide by 3 or by 2. That's the difference. When you have 1,000 values and you divide by 1,000 instead of 999, that makes nearly no difference. But for measurement and instrumentation, we have never an infinite number of measurement values, and therefore we have every time to divide by n-1. And when you look on your pocket calculators, I make a new when you look on your pocket calculators, German calculators make it very exactly. You have the standard deviation. That means n-1. You divide by n-1. And for the mathematicians, you have also the sigma. That is divided by n, but under the condition that n is going to infinite. And that is only useful for mathematical things. For practical things like measurement and instrumentation, you have every time to use this. And when you have pocket calculators from the English or American area, they write in many cases sigma n-1. That sigma n-1 is the same like this. It's the same like we make in Germany a difference between S and sigma. Sigma means n against infinity, and S means a sample. The same we have with the mean. In Germany, we say this is a mean from a sample, and this is the mean when n is going infinite. What is the difference? You have a measurement raw, and you have measured many times. And when you calculate for the mean, the so-called running mean, you calculate the mean between these two, then you calculate the mean between 3, then you calculate the mean between 4, and so. Then you see that you are going in such a tube, and the difference will be smaller and smaller. It's difficult to draw. This will be smaller and smaller, but when you cut here, when you stop your measurement, you have here an mean plus minus a delta mean. That is a delta mean. And this delta will be smaller and smaller when you have more measurements. And when you go with your measurements against an infinite number, then it is very difficult to draw on this tablet. Then you go to the expected value of the mean. And the expected value of the mean has no plus minus. That is the difference. This is a theoretical value because in the practice, you can never have an infinite number of measurements. That is the expected value, what you would like to have, but what you never get because you cannot measure an infinite number. But when you stop your measurement anywhere, then have you a rest of difference, because the next value, what you calculate here is maybe the mean what you calculate is here, but with the next value, the mean is here, and it is inside of this tube. And when you have more measurements, maybe here you have 100, here you have 1000, then is the difference much more smaller. But also here you have an mean plus minus a delta of the mean. The delta is much more smaller than here, but there is also a delta. And this phenomena you have also with the standard deviation, because in the standard deviation you calculate also a mean inside, and therefore when you have an infinite number of measurements where we speak from this sigma without a plus minus, when we have an limited number of measurements, what we have every time in practical measurements, then have you a plus minus also from the standard deviation. It's the same phenomena. Have you questions? So I must look for my mouse. We go back to the lecture. Yes, that was this what I have you explained. Here we have the squares of the difference between the mean and the single value. It makes no difference. You can say the mean minus the single value, or the single value minus the mean. Here is only written the difference, and when you power by 2, it is all plus in the end. That means it makes not a difference if you say yi minus the mean, or the mean minus yi, that is the same. So, and then we calculate the mean over this powered by 2 differences, and that is the variance. The variance is already a quality parameter, but it is not so useful for us in measurement and instrumentation, because the variance has a powered by 2 unit of the unit what we measure. And therefore we take every time the root, and then have you the standard deviation. And the standard deviation has the same unit as your measurement value, what you have measured. By the way, when you look for the right formula on your pocket calculator, you can use this trick with the 3 following numbers, 15, 16, 17, or what else. 3 following numbers. And when you calculate the standard deviation for 3 following numbers, you must get exactly 1.0. Then have you the right formula, because the mathematicians have also some other formulas under other conditions. For example, the sigma when n is going to infinite, but that is not useful for our practical applications. When you would like to check that you have the right formula, please put in 3 following numbers, calculate the standard deviation. When it is 1.0, then you have the right formula for the standard deviation. So now, of course, is a question, how many of the values are in this range. You can now say we have here the mean, we have the normal distribution over this mean, and when we integrate over this area, and that are the number of measurement values under this curve from mean minus s to mean plus s, then have we 68.3% of the measurement values under this curve. That means when you say, I go back in my drawing, that means when you measure 3 centimeter and your standard deviation was 1 millimeter, that means between 2.9 to 3.1 centimeter. In this range are 68, what's now? 68% of the measurement values. 68% of the measurement values are in this range. And when we double the S, when we say 3 centimeter plus minus 2S, plus minus 2S means plus minus 2 millimeter in this case. That means between 2.8 to 3.2 in this range, you have 95.5% of the measurement values. I go back. You see it here. The range is bigger, but you have a higher number of measurement values in. And 3S means 99.7% of the values are in this range. This is valid for micro and the standard deviation, but the sigma, both with n against infinite. But because we can never measure an infinite number, we take it also for S and Y. S for sigma, the mean for the expected mean. When you calculated this mathematically, you can let run the n against infinite, and so you can calculate also this percentage, but that is all calculated already. You can look in tables where it is written, also with 4S, 5S, 6S, and so on. But because we can never determine the micro, the expected value, because we cannot measure an infinite number of measurements, we take it also for S and the mean. And therefore is here written for enough big N. This context is also nearly valid for S and the mean. What is enough? That is a very good question, but for the industry, we say roughly 200 measurement values. When you have 200 measurement values, then can you say the difference between S and sigma and the difference between the mean, the empirical mean, and the practical mean and the expected mean is also nearly nothing, so that you can say when you have 200 measurement values or more, then you can take it for each other. So, and by the way, I have written here a remark. We have the dot and the comma is every time a problem. In German, we say 68.3. This is the same as English 68.3, but we write it with a comma. And in German, it is 11,000,2. In English, 11,000.2. That means the dot and the comma is changed between German and English. I think in French it is the same as in Germany. In Russia, I think it's also the same. When I'm wrong, please say it. But I think in Russia it's the same. But in Malaysia, I think you have the English writing. I have some drawings also from my German lectures, and therefore in the drawings I have not changed it. That means 99.7 in English. It is very important to know that the comma and the dot is right, especially when we work in our lab with Excel. We have the German and we have the English Excel, and when we write it wrong, you get also wrong results. So then another point, we have calculated this standard deviation from the past. We have measured many times, have calculated the standard deviation, and have made this drawing. And the question is, can we also make can we also speak about the future? And that can we. I will explain it in a drawing. A new one. We have in the past, we have measured many times. We have calculated mean, and we have calculate the standard deviation. That is the standard deviation plus minus S. And in the past, we said the mean plus minus S. In this range, we have 68.3% of the measurement values. The value, what we take for the true value is the mean, because the mean has the highest probability. And therefore we say, for us, the mean is possibly the true value. And when you measure a single time, for example here, a single time in the future, and you write the standard deviation plus minus S around this single value, this is a single value, plus minus S, plus minus S, then you can say the true value, the mean, the true value is also with 68.3% possibility around in this range. This is the view in the past, and this is a view in the future. In the past, we said y, that means the mean, plus minus the standard deviation in this range was in the past 68% of the measurement values. But we can also say for the future, in the range of a single value, what I measure, in the range of plus minus s around the single value is the mean, the true value, with 68.3 of the possibility. One is a look in the past, and only from the past we can calculate all the values, but this is the look for the future. And that is important, especially when you use your measurement values, for example, for controlling something. When you have a closed loop control or something, then it is important that you say the true value is with a high possibility in a small range about my single value. When it is not the case, then, for example, you have to measure 2 or 3 or 5 values and take the mean and calculate it then, so that you have a stable output signal. Have you questions? Okay, then we come to the question, the average error of the mean. That is this, what I have told you when we measure a running mean. I go back in my drawing, then I can explain it a little bit better, I think, to you. We have this measurement values, and you have calculated the running mean. The running mean, the tube will be smaller and smaller and smaller. And anywhere you say, I stop, I calculate my mean. And now is the question, what is this difference? How big is this difference? This is depending from the standard deviation. That means that this difference is, of course, bigger as when you have such a small standard deviation. Then is the difference from the beginning much more smaller. That means the standard deviation has a big influence. And then you have a decrease of this difference with a number of measurements. If the number of measurements is higher, you get a smaller difference. And that is running with the root of n, with the root of n. So when you have a higher number of measurements, then is it smaller. Sorry, I have written it here. That means the delta, of course, the delta of the mean is the standard deviation divided by the root of n. And now we have seen that the standard deviation has also a plus minus. And mathematicians have calculated that the plus minus of the standard deviation increase this delta when you have a lower number of measurements. And that is running by the t factor from the student distribution. The t factor from the student distribution is an add-on for this plus minus. And when you look in this table, you have here n, the number of measurements, You have here the statistical probability, how many measurement values are in this range. That is 1s, 2s, 3s. And when you have more than 200 values, therefore I have told you more than 200 values, you can take the S for the sigma, and you can take the mean for the micro. You see over 200 values. This is 1S. 95.5, that is 2S. 99.7, that is 3S. But when you have lower number, sorry, I have forgotten to translate this word. That means more S, that is German. More than 200 means this. When you have lower numbers of measurements, your standard deviation get an uncertainty, an additional uncertainty. And therefore, this T is not 1, 2, 3. This T is a little bit more. And you see, when you have only 5 measurements, you calculate not with 1S, you calculate with 1.15S. And when you want to have a probability of 95%, you calculate not with 2, you have to calculate with 2.88. And this 88, this is an add-on for the uncertainty of the standard deviation caused by this low number of measurements. And of course, when you want a very high probability, a very high security with 99.7%, and you have only 5 measurement values, then have you to calculate not with 3, you have to calculate with 6.62. You get then this probability, but you have a huge range where you are, because you have only 5 measurement values. Important is this every time I go back. When you compare two experiments, for example, let me say a German group has done an experiment with 100 measurement values. And another country, let me say in Malaysia or in Russia, they would try to repeat this experiment, and they have done also 100 measurements, also 100, and they get a value from the mean from, let me say, 1.2 voltage or what else, and they get a value from 1.4 voltage. And now is the question, is this the same? Is this the same measurement row? Is this only caused by the natural scattering in this measurement row, or is it another measurement equipment or another measurement row? Have we done something different? And then you calculate for the measurement rows the running mean. You calculate this delta y. And when both values are in this range, 1.4 and 1.1, when both is in this range, then can you say both measurement rows are the same? This is only a difference from the scattering inside of the measurement rows. But when you say 1.2 is here and 1.4 is here, then you must say this measurement row is different from this one. That is not the same experiment. This is a different experiment because that is outside of the range of the natural scattering of this measurement row. And for this, is this calculation important when you compare, for example, two measurement rows? Have you questions? Okay. So then only some expressions what I would like to explain. The accuracy class. Let me say, what we have done until now is the scientific expression of the measurement error. But in practical applications, it is often so that the people in the factories or in the companies, they want not a difficult explanation of the error with a probability, but the scientific explanation of the error with a probability is the only once mathematically based expression of the error. That's the scientific method, what we have done until now. But in many cases in factories also, they want only one number, and this number should express what is the biggest error in percent of the measuring range from a device. What is the biggest error? When you have a measurement device for voltage, 100 volt, 0 to 100 volt, they want to know what is the biggest error with 100%. What is the biggest error? And for this, we have so-called accuracy classes. Very typical accuracy classes, for example, in electrical measurement devices are 1 or 1.5. This means 1% of the measurement range. That means when you have a measurement range from 0 to 100 volt, you have plus minus 1 volt measurement error. That's the maximum. That is very easy to express, very easy to understand, and therefore in the practice it is used, but it is not the scientific method, because the scientific method is every time coupled on a probability. And that is here not the case. I have an example here, a voltage meter, accuracy class 1, 0 to 100 volt. By displayed 100 volt, the maximum error is plus minus 1 volt. But when you display 10 volt, the maximum error is 10 volt plus minus 1 volt. That means the relatively error is increasing to the lower side of the measurement range. And from this fact is coming the requirement to use the range so much as possible. In the practice, we say, if possible, the last third of the range is to use. For the last third, there is no reason that it is exactly the last third. You have to use so much as possible the range, because the relatively error is in the end of the range smaller as in the beginning of the range. And important is the accuracy class is a compromise of an exactly error analysis. So as we have had it with the standard deviation, mean and standard deviation and so on, and, and an easy usability. Therefore, in many factories and many companies, they use this accuracy class because it is very easy. It is easy to understand, but it is not the scientific method. And when you have companies who work in a range of high production of high-end products, they use not the accuracy class, they use the standard deviation, mean, standard deviation, and so on, with the probability of the error. So I think, yeah, we are nearly on the end, and I think I make now also a break. What we have learned now was the description of the random errors. You have seen we have systematic errors and random errors. The random errors we can only describe. We don't know them when they occur. We don't know the amplitude. We don't know the sign. When one of this is not known, it's already a random error, but mostly nothing is known. And then can we only describe the scattering of the measurement values. In the next lecture, we will start with the systematic errors. And the systematic errors are errors where we know all this. And when we know all these points, the amplitude, the sign, and when they occur, when we know all this, then can we correct these systematic errors. And that is what we call calibration, or what we can call computer-aided calculation of measurement results. There are different expressions for, but that is what we start in the next lecture. For today, I finish. I wish you a pleasant day. We have a fantastic weather. The whole week should be fantastic weather. And the students who are present in Osnabrück, we will meet us in the end of the semester, then in the practical work in the laboratory. But until this time, please use the time to discover Osnabrück, to discover Germany. And I hope you have a lot of fun also when we make this